Good day, Mr. Darren and everyone. My name is Zhang Xinrong, and my student ID is MAT 2509035. I'm a student at Xiamen University, Malaysia. Today, I'm excited to present my project for our Algebra and Analytic Geometry course. The topic I have chosen is Rules of Unity and Layer Symmetry. Why did I choose this topic? Because in mathematics, we often see algebra and geometry as separate fields. However, the rules of unity are the perfect bridge that connects them. In the next 10 minutes, I will guide you through 4 key parts. First, we will define the rules using the general formula. Second, we will look at a concrete case study where n equals 3. Third, we will visualize the beautiful geometry behind these numbers. And finally, we will prove this most important property, symmetry, using both algebraic proof and physical intuition. Let's start with the definition. What exactly are the rules of unity? Mathematically, we are looking for complex numbers z that satisfy the equation z to the power of n equals 1. If we were only working with real numbers, this would be boring. For even numbers, the answer is just 1 and negative 1. But in the complex number system, the fundamental theorem of algebra tells us there must be exactly n solutions. So, how do we find them? We recall the exponential form of complex number from chapter 5.3 of our lecture notes. Z equals R times e to the power of I theta. Since the modulus of 1 is 1, our radius r must be 1. The real magic happens in the angle. We know that 1 can be written as e to the power of I times 2 pi k, because rotating by 2 pi brings you back to the start. By taking the n root, we derive the general formula using on the screen. Z sub k equals e to the power of I times 2 pi k over n, all in trigonometric form. Cosine of 2 pi k over n plus I times sine of 2 pi k over n. Here, k is an integer from 0 to n minus 1. Essentially, what we are doing is dividing the 2 pi circle into n equal slices. To make this abstract concept concrete, let's look at a specific case, the cube rules, where n equals 3. We are solving z cubed equals 1. According to our formula, we need to divide the full circle of 360 degrees, or 2 pi radians, by 3. This gives us an interval of 120 degrees, or 2 pi over 3 between each root. Let's calculate them one by one. First, when k equals 0, the angle is 0. E to the power of 0 is simply 1. This is the trivial root. Second, when k equals 1, we rotate by 120 degrees. This gives us z sub 1 equals negative 1/2 plus I times root 3 over 2. Third, when k equals 2, we rotate another 120 degrees to 240 degrees. This gives us z sub 2. If we went to k equals to 3, we would hit 360 degrees and be back at 1. So algebra tells us the values, but what does this look like geometrically? This brings us to the Argand diagram. I use Python to generate this visualization for the case of En equals 6. Please look at the graph on the screen. There are three key observations we must make. The unit circle. Notice that every single blue arrow tips lies perfectly on the dotted gray circle. This confirms that the modulus z is always 1. Regular polygon. If we connect these points, they form a regular hexagon. If n were 3, it would be an equilateral triangle. If n were 4, a square. This is a fundamental geometric insight. Roots of unity are the vertices of regular polygons centered at the origin. Equal spacing. The angle between any two adjacent vectors, say omega 1 and omega 2, is exactly 2 pi over 6, or 60 degrees. This visual representation is powerful because it reveals the hidden structure that the algebraic equation z to the 6 equal 1 doesn't explicitly show. Now we move to the most fascinating property of list roots, their sum. Intuitively, looking at the symmetry, we might guess the sum is 0, but as mathematics students, we must prove it rigorously. Let omega equals e to the power of I times 2 pi over n. The root can be written as a geometric sequence 1 omega, omega squared, up to omega to the power of n minus 1. We want to calculate the sum, the summation of z sub k. From our lecture notes, we know the sum formula for a geometric progression is S sub n equals the first term times 1 minus the ratio to the power of n divided by 1 minus the ratio. Substituting our values, we get 1 times 1 minus omega to the n over 1 minus omega. Here is the key. Since omega is an nth root of unity, by definition, omega to the power of n equals 1. Therefore, the numerator becomes 1 minus 1, which is 0. Thus, for any n greater than 1, the sum of the roots is exactly 0. We have proven it with algebra, but I believe the best way to understand it through a physical intuition, what I call the physics of symmetry. Let's go back to the Argand diagram. Instead of thinking of them as numbers, imagine the orange 0, 0 is a physical object, and each root is a force vector pulling on it. Because the roots form a perfectly regular polygon, the system is rotationally symmetric. There is no preferred direction. If the sum of these forces was not 0, it would point somewhere. But why would it point to omega 1 and not omega 2, given they are identical in arrangement? Nature loves symmetry. The only vector that has no direction is the 0 vector. Therefore, purely by the argument of symmetry and balance, the forces must cancel out. This explains why the sum is 0. Symmetry dictates balance. To conclude, the roots of unity are a beautiful example of how mathematics connects different worlds. We start with an algebraic equation z to the n equals 1. Visualize it as a geometric polygon on the complex plane, proved its properties using theories, and understood it through physical symmetry. I hope this presentation has given you a clear understanding of this topic. Thank you very much for your listening.